So this lecture is going to talk about polarized glasses and then just some odds and ends about light. So I wanted to talk about polarized glasses because even though your textbook doesn't talk about them, I know some of you wear polarized glasses and some of you work with things like polarizing lenses. And so I wanted to show you what the science is behind how these work. I actually have polarized lenses in my glasses. You can't really tell right now. They're the ones that actually change when they're exposed to UV light. But they are polarized, and so they will work the same way as what we're going to see here. So first, the thing we have to think about is what kind of wave does light travel in? And so if we remember, light travels in that transverse wave, right? It does the wave kind of like the wave on the water. It does the up and down type of motion. And that's important to understand how polarization works, because polarization only happens to light waves, not sound waves. And that should make sense as we go through this, because remember, sound waves are not transverse waves. They're those longitudinal waves, the ones that squish and expand. And so this polarization won't work on longitudinal waves. It only works on transverse waves. So let's start with what unpolarized light looks like, what's going on. So unpolarized light is basically the light that's just coming in from any light source. The vibrations producing the light are going in all possible random directions. So for example, the light that I'm using here with my recording, it's coming straight at me, right? So the waves are coming straight at me. That's the direction of the light rays. However, the vibrations are going to be going in all different directions. So let me get my diagram up here to show you. So you can see that those light rays are going forward, but what I mean by the vibrations is that up and down motion. So we have waves going up and down this direction, up and down this direction, up and down this direction. So they can go in any of those directions, plus anything in between. On the other hand, polarized light are just waves vibrating in one direction. So you can see that the light is going forward, just like with unpolarized light, but all of the waves are traveling together in one up and down motion. So in this case, they're all going straight up and down. Right, so what does that mean? So we've got unpolarized light that's coming in, and let's take a look down here at the example with these pallets. So we've got these wooden pallets, they've got slits in them, and they've run a rope through them. So the rope is like the light. Now, what we've got is light, in this case, that is traveling in that up and down motion, right? And so it is what we would consider, because it can travel through these pallets, vertically polarized. So it would be what we see up here in A. We've got unpolarized light traveling in all the directions, and then the pallet, or a polarizing filter, is only allowing the vertically polarized light to travel through. So that vertically polarized light can travel through, and because the second filter is also doing vertically polarized light, it will also allow those light rays to come through. Then if you look at the second one, we've still got that filter who's allowing vertically polarized light to go through, but then the second filter has been turned 90 degrees, meaning now only horizontally polarized light would be able to come through. Only light rays that are moving in that horizontal plane would be able to make it through. So you can see with the rope, that actually stops the movement. And up here on B, that's what we're seeing with the light. So we've got unpolarized light, it goes to the first filter, vertically polarized light, so we've got up and down. Then it hits the second filter, and it's horizontally oriented, which means that these light rays can't make it through there. And so out the other side, no light rays. And so that's what you're seeing over here. So A is A over here. It's allowing vertically polarized light through, so that's why we can see her, but not like we would normally see her. There's not as much light traveling through because it eliminates some of the light rays from the unpolarized light. But then at B, she's turned one of those filters 90 degrees, and now you can see there's a block where there's no light coming through and it appears black. And that is because all of the light rays are now being blocked to make it through that section. So how do lenses in, for example, polarizing glasses or a polarizing lens in a camera works? So what happens is you're usually using those glasses or lenses when you're working with something like water. And so water will polarize light because what happens is the sun comes in, it's unpolarized light, the sunlight hits the water. Now it's transparent, so some of it will actually get absorbed, but some of it will get reflected, especially depending on the time of day. The light that's reflected is going to be horizontally polarized. So it's going to bounce off of that surface and it's going to be horizontally polarized, and that's what's going to come towards your face. And so what do polarizing lenses and polarizing glasses do? They are going to be vertically polarized in order to block that horizontal light. So you can see there's the incoming light. It has horizontal light and vertical light. And there's that polarized lens that would be in your camera or the glasses. And you can see that it's polarized for vertical light only. And so it's going to cut out that horizontal light, which is going to be a lot of that light coming off of the water, and only allow any vertical light to come in. That's why you don't completely have a blacked out area in front of you, but it reduces that amount of light coming off of the water. And so that's why you get this different view. So here, this is what it looks like with a polarized lens or polarized glasses versus without them. So you get that glare because you're getting that horizontal polarized light off of the water. So I said that there were a couple of other random things that I wanted to talk about related to light. One is sunsets. So sunsets are actually one of my favorite things related to light because there's two properties that are related to these guys. One is related to refraction, and that is because when you see the sun set, it's actually well below the horizon. So at sunset, you're not seeing the actual sunset. The sun has set well before then. And so if you take a look here at this little sketch, so it looks like the sun is right at the horizon at sunset to you. However, the light is being bent. The true position of the sun is below the horizon because the atmosphere of our planet is going to refract or bend those light rays towards you. And so a cool thing that you can do if you're ever on the west coast of the United States, especially like the beaches of California or Washington, is to lay on the beach. So lay down flat on the beach with your head just up a little bit and watch the sunset. Once the sun has set, jump up because you can actually watch the sunset a second time. And it's because of this property. That refraction allows that bending of light, and so that little bit of height difference will actually allow you to watch the sunset for a second time. The other thing that is related to light is, why is the sky blue during the day and why are sunsets that red-orange color? And so it has to do with a process called selective scattering. So in other lectures, I talked about selective reflection and selective transmission. Here, it's selective scattering. So what am I talking about? Well, our atmosphere is made up of particles, right? It's made up of nitrogen gas, oxygen gas, carbon dioxide. We don't think about them as having mass and interfering with things, but they do. The light rays are going to run into those particles as they come into our atmosphere. And so what happens is that as the light comes in, it's going to hit these particles and molecules and get scattered. And some of those light rays are going to get scattered more easily than others. Violet and blue get scattered more than oranges and reds. So the higher energy portions of the visible spectrum are going to scatter more than the lower energy ones. And so during the day, the reason why the sky is blue is because, as you can see here, we get the light rays coming in, and so the red, oranges, yellows are going to come, and they're not going to get scattered. They're not going to get bounced off of those molecules very much, and they're going to come straight down. So we won't see them. They'll hit the things on our planet, and they'll help us see colors and so forth. But the blues and the violets are going to bounce off of the molecules in the atmosphere more. And because they're bouncing around, we can see them up in the atmosphere. And so it makes the sky appear blue. It doesn't make the sky appear violet because we can't see violet very well, especially violet light. If you've ever had pointers, laser pointers, you may notice that the green ones are actually the ones that we see the best, and that's because for our vision spectrum, green is the best color for us to view. Red is better than violet, but green is the best one. It's going to appear the brightest even if they're all made to be the same strength as far as the light coming out. So that's why skies appear blue, because during the day, when we look up, we see that blue light being bounced around inside of those molecules in the sky. At sunset, now the sun is coming straight at us. It's pointed straight at us. So the blues and the violets are still being scattered, but they're being bounced away from where we're looking. And those reds, oranges, and yellows are pointed straight at us. And so that's why those colors are what we see show up most often in a sunset. So then the last question is, why are clouds white? Well, clouds are white because they are made up of tons of water droplets. And so when the light hits one of those clouds, all of those light frequencies bounce around inside of them and basically end up lighting them up because they just bounce around and reflect and refract inside of them. And so they end up just keeping all of those light frequencies, lighting them up and making them white, since they are all going to show up and scatter inside. So that's the last of the light information for this section, and it's actually the end of the physics section. So the next section we'll be looking at is chemistry.